right. All right, so this is math 111Z, section 2.5 in the text, part 2. Excuse me. Okay, here we go. So we're going to talk about the average rate of change, which is also known from your great time in Algebra 1 as the slope. So AKA, also known as, its street name, the slope. Right? The average rate of change, or the slope, which we often denote with an M, is y2 minus y1 over x2 minus x1. Change in the y's over the change in the x's. Might have learned that as your rise over your run. In function notation, it looks like this. F of x sub 2 minus f of x sub 1 all over x2 minus x1. Because this is just the y at x2, which would be y2, and the y at x1, which would be y1. So this is how you would write that difference in the average rate of change. Now we're talking more about an average rate of change instead of a slope, because a slope makes a lot of sense when your rate of change is constant, meaning it's a line that always goes up the same amount each time. So this would be a line which has a constant rate of change. But if we look at other graphs, something like this, we can talk about an average rate of change, which is the amount of change it averages, say from here to here. So from this point to this point. You notice that this is not going to be constant. Like this rate of change, this slope, is not always the same. If I pick two different points, I have a very different rate of change. It's going to be steeper. It could also be even negative, depending on which points I choose. So between this point and this point, on average, the function goes down. Between this point and this point, on average, the function goes up. So the average rate of change on a nonlinear function is not going to be constant. Let's take a look at a couple examples with real numbers. Let's say I am looking at the rate of change for the function 2x squared plus 1 on the following different intervals, from x is -3 to -2, or the interval 0, 2. So two different examples. So the rate of change here, if I put in f of -3 minus f of -2 all over -3 minus a -2. So on the bottom, I'm going to have -1. On the top, if I put -3 here, I've got -3 squared, which is 9, times 2 is 18, plus 1 is 19. -2 here, I've got -2 squared, which is 4, times 2 is 8, plus 1 is 9. So this would be 10 over -1, or -10. So my average rate of change, it goes down 10 for every one over in that interval.
What's the f of x equals 2x? 2 plus 1.
Yeah, how'd you get the 19 minus 9 on that?
Yeah.
So let's take a little this one. F of -3 is equal to 2 times negative 3. Everywhere I see an x, I put a negative 3 squared plus 1, which is 2 times positive 9 plus 1, which is 18 plus 1,
Oh, okay.
which is 19. Likewise, f of negative 2 is 2 times negative 2 squared plus 1, which is 2 times 4 plus 1, which is 8 plus 1, which is 9. So essentially, I am plugging my two endpoints from my interval into the function that they gave me to analyze. Right? Doing example 2, same idea. We're going to take f of 0 minus f of 2. It doesn't matter which way you do it, as long as you're consistent. 0 minus 2 on the bottom. 0 minus 2 on the bottom is negative 2. On the top, when I put 0 in here, I get 0 plus 1, which is 1. Minus, when I put 2 in here, I get 2 squared plus 4, or 2 squared is 4. Times 2 is 8, plus 1 is 9. So this is going to be negative 8 over negative 2, which is 4. So my average rate of change here is 4. Okay. Let's take a quick look at what this graph looks like. And then kind of plot out what's actually going on visually. Okay, so we were looking at that interval from 2 to 3, and I just want to show you the graph of this and why that rate of change was 10, that average rate of change. You see, if I go from this point to this point, I go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 down, and 1 over. So my average rate of change would be 10 over negative 1, rise over run. Sorry, it should be negative 10 over positive 1, which, because I'm going down 10, which would be negative 10, which is what we just had in that last slide. Okay, again, looking at the second example where we had that average rate of change of 4, here we had, let's see, 0, 2. You can't see the 0, 0 on here very well. So let's grab a different image of it. Okay, and so we're going to take another look at this other picture where we had the 0, 1 point. And if I look at what our average rate of change is, I'm going over 1, 2. That's 2 over. Each one of these is a half. This is up 1, up 2, up 3, up 4, 5, 6, 7, 8. Right? So my average rate of change would be 8 divided by 2, which is our 4. All right? So now that doesn't mean that the rate of change is always 4. If I go over 1 here to this point, it's not 4. It's 2 over 1, which is 2. So you see the rate of change changes based on the points that you pick. It's not going to be the same line because it's not constant. If it was constant, it would be an actual linear function. So that brings us to this next part, which is something called the difference quotient. And we use the difference quotient extensively in calculus. Basically, we say something like this. Suppose you have a function, and it looks like this, blah, blah, blah. It can look like any curve you want. And you pick a point right here. We'll call that point x. And we go h over. We move over h. Then this point over here is called x plus h. So you notice we went over h. Then we just figure out the rate of change, the average rate of change between x and x plus h. So it would be f of x plus h, that's the y value. That would be this value here. This value here, right here, is f of x plus h. Minus f of x. That's this value here. So that quotient, or difference, represents your rise. And then your run is this here. We just want h over. So it's h. That is the difference quotient. F of x plus h minus f of x all over h, the difference quotient.
For a second.